Hello, I'm Abhishek, and together with Bala, we'll discuss how we tackle DC congestion and bursts in the Meta network. We both are part of the networking infrastructure org at Meta. We hope this talk will be useful for those who are interested in solving similar challenges. Here is the agenda for our talk. We'll discuss scales of DC congestion using data center TCP, service-specific microbursts that happen, receiver window tuning, and some next steps. In our network, TCP is the network transport protocol that supports thousands of services. These services exchange a lot of data and sometimes have competing traffic as well as bursty behavior. This leads to network congestion where the links are asked to carry more traffic than they can handle. In our network, we observe congestion at primarily two timescales: timescale of around tens of milliseconds and timescales of a few milliseconds. For tens of milliseconds, we are using congestion control tuning, and for a few milliseconds, we're using flow control tuning. As part of this talk, we'll see how these techniques are complementary to each other. Now, TCP, in order to be able to react to congestion, needs a congestion signal. Largely, these are the major ways in which TCP can get a congestion signal. First, using packet loss. Any loss of packet can tell TCP that there is congestion in the network. Another way could be delay-based, where a delay comparing the round trip time of the previous packets to the next can tell us that there is congestion because the packets are arriving later. Another way is using ECN, which is explicit congestion notification. It requires hardware support, but network devices in the path can both identify and indicate congestion in this case. For our network, we went with data center TCP, which uses ECN-based mechanism for congestion signal. Let's see how this works. In this diagram, we see two servers that are communicating using a switch, which is a network device enabling this communication. The switch also has queues which carry data. Now, the switch supports multiple hosts at the same time, as well as multiple connections from the same host. When the sender sends some data, it would get queued in these switch queues. The switch also supports ECN in this instance, where it has an ECN threshold, where if this threshold is breached, it will send an ECN notification notifying that there is congestion. We worked to identify this ECN threshold, which will be good for our network. Now, we see that the data is queued, and then when the data is to be relayed, the data plus the ECN bit is set on this. This tells the other end that there is congestion identified. Now, when this data is to be acknowledged, the ECN flag is sent back to the original sender, telling it to slow down. Within our network, we have data that is exchanged both within the data center as well as across data center. Data exchange within the data center is intra-region traffic, and data exchange across regions is inter-region traffic. We use DC-TCP only for intra-region traffic because the latencies are predictable and we know that the congestion signal will be delivered in a predictable amount of time. For inter-region traffic, we continue to use congestion control, which relies on packet drops as a signal. To enable this, we have two different thresholds on the switching queues. First one is the ECN threshold, which we discussed previously. Another one is a tail drop threshold. This threshold is for inter-region traffic, whereby if this threshold is breached, we will drop packets on the rack switch queues so that the congestion signal can be delivered. Now, supporting multiple congestion controls in the fleet brings complexity in how we can enable it. We had a few choices on how we wanted to enable DC-TCP. Let's review them. The first one was using route, where we need to program node-specific routes for choosing DC-TCP for all intra-region routes. This was difficult to do because it would have required us to implement host-specific configuration. Another approach was using sysctl, but sysctl does not support specifying multiple congestion control at the same time. Yet another way was using setsockop, but it would mean that every service will have to use setsockop and perform the implementation on their own, as well as for any changes, it would require that all the services would have to make that change. Another approach was using cgroup BPF, which allows us to create a custom selection BPF program. It requires some dependencies to be met, which are for the minimum kernel version and cgroup v2. But provided these dependencies are met, the logic can be completely customizable on how we want to select congestion control algorithms. In our case, we went with the C group PPF approach and implemented a custom congestion control selection PPF program which would select DCTCP for all the intra-region flows. During the initial parts of the rollout, we saw something interesting. We saw that the SYNAC packets were not getting the ECN treatment, and it resulted in high latencies for one of our major services. The chart on the right shows how these timeout events increased soon after the rollout and died down with the fix. We identified that this was happening because of a kernel bug, where the SYNAC packets were not getting the ECN flag set. The fix was identified, but it would have meant that we would have to roll out a new kernel to the entire fleet in order for that fix to be made available, and live patching was not an option for us back then. Ultimately, we ended up creating a new BPF program to explicitly mark the SYNAC packets so that we can resolve this. Once the bug was fixed in the kernel, this temporary BPF program was removed. Another important aspect for us was to understand the performance of DCTCP. We measured the adoption rate of DCTCP to see how quickly it is being adopted in our fleet and found out that for short-lived connections, it can take a few milliseconds for the connections to be replaced using DCTCP, or it could take up to weeks for the connections which are long-lived for them to adopt DCTCP. Another aspect was to identify whether the improvements that we are seeing in the network were attributable to DCTCP or not. For this, we created a control signal using the regions which did not have DCTCP deployed and compared it with the region of a recent deployment. Here, in the diagram, we see a control signal for retransmission events created using three different regions. The control signal is fairly static, and up until the DCTCP deployment takes place, the rollout region also follows very closely the control signal. Once the deployment takes place, we see there is a great reduction in the retransmission events. This proved to us that the improvements that we are seeing in the network were because of DCTCP. We also saw some network-wide wins, like the reduction in rack switch discards by 91.5% in the fleet. The diagram below is a time-aligned diagram which has stacked all the regional rollouts together on the same timeline. Here, we see a large number of rack switch discards, which then reduce after the DCTCP deployment. Now, we know that rack switch discards are basically packet drops, which also cause retransmission for those packets. By reducing the rack switch discards, we also reduce retransmissions, and therefore we reduce the congestion in the fleet. For some bursty services, we also saw some great wins. For example, Feed, which is a service which creates the newsfeed for all the users on Facebook, we saw a reduction in P99 object fetch latency. The diagram on the left is a day-over-day comparison of latencies from the previous state. We see here that right after the DCTCP rollout, there is a great reduction in this latency. Similarly, for search service, which powers all the search on our platform, we see a reduction in tail latency. The diagram on the right indicates the percentile view of the reduction in tail latency at various percentile levels. Next, I'll hand it over to Bala, who will cover handling congestion using flow control.
Thanks, Abhishek. Thanks for going over the timelines of at which we see congestion in our data center and how DCTCP helped us to tackle them. Now, I'm going to go over a bit more granular timescales at which we see congestion, and I would want to share a solution that we built and deployed in our fleet. First, let's look at what happens at millisecond level granularity on a host in our network and try to see what happens. When it starts receiving data, the ingress rate goes up from 0% to 100% of the line rate in a very short span of time, like 2 milliseconds. And let's see what happens next. Okay, we have DCTCP running, so the ECN signal quickly catches up with the ingress rate, tries to slow us down the sender. What do you think should happen right after this, right? In an ideal world, yes, ECN should have slowed down the sender and we should have handled the congestion without any drops. But if you look at what exactly happened during this burst, is we did see quite a good number of retransmissions within this burst. And now why is that? The answer actually is on the time scales of this problem. If you look at the overall time, of the burst, it's actually only 10 milliseconds. So what happens at these time scales is that the signal to slow down the sender is much slower than the send rate at which the sender can send the packet out, which means that the burst would have already left the sender even before the ECN signals could go ahead and slow them down to make sure we don't see the retransmissions, right? So these types of bursts are called microbursts. And let's see how this, what are the actual problems that are causing this kind of microbursts. To understand this problem, we need to understand what is window in TCP. This is one of the core concepts. So a window is the number of packets that you can let out without getting an ACK, right? So this decides the speed at which you could go ahead and transfer your data, which is very important, right? Let's try to calculate what is a good estimate for a window value for a flow that's within the region, right? So this leads us to calculate the BDP of or the bandwidth delay product of a specific flow in region, right? Let's say we want to saturate a 10 gig receiver, right? And with RTTs for in region flows around 100 microseconds, this value comes up to around 125 kb, which translates to a very few number of packets actually, right? And this is considering 100 microseconds. Think of in rack flows just taking like less than 50 microseconds, right? Which means that your receive buffer or your receive window should not be more than 64 kb. So, and on top of this, we are talking about one receiver trying to saturate a 10 gig NIC. Just assume what should be this value if you are going to share the NIC across multiple flows, right? So using this theoretical value, we tried to do an analysis on the top 25 services in Meta to understand where or what the exact window value for these flows are. And pretty interesting, we figured out that 40% of the services are actually having windows much larger than what a receiver needs to handle data with minimum queuing. So what this tells us is congestion, just you depending on congestion control algorithms alone doesn't help us to limit our windows to a safe value that could not let retransmissions, queuing to happen, right? Let's look at another problem. So this is a pretty common problem called the incast problem, and I'm going to take one service architecture where this happens pretty common. So let's say we have a service that receives a request. It's immediately going to try to reach its subsequent services to get the responses back, or maybe get it from a shard stores or anything, right? So now see what happens when the response comes back. The receiver, or in this case the aggregator, is actually choked and his NIC is overwhelmed by the number of packets that's received from all the responses that he had queried for. So this is one this causes P99 latencies for services to spike, which is one of the key parameters services actually rely on. Again, if we can't go ahead and control or change service architectures to redesign this, but what we're trying to say is let's try to avoid persistent queuing for in normal situations so that we could actually have some space left for absorbing burst that is not under our control, right? Okay, both these problems, right? We looked at two problems. Both these problems actually guided us to create a solution that is basically complementing the congestion control algorithm and also makes the receiver handle traffic characteristics that are in CAST, right? And this is where receiver window tuning comes in. So what receiver window tuning does is it tries to limit the window advertised by flows based on the BDP characteristics as well as based on the traffic profile seen on the receiver. We figured out that, as you can see in the second problem, the receiver is the one who's actually knows what is the rate at which he can receive data when compared to the senders who could try to send them as fast as possible, right? So, and unlike tuning your buffers, window tuning is pretty isolated to the network, and it just controls the number of packets in flight and doesn't change your buffer values. So Let's see how we were able to implement this solution in our fleet. We basically use the flow control knob of the TCP to try to limit the maximum flows to the BDPs or something closely tied to the BDPs. We had our own BPF program that runs at the egress that tries to rewrite each packet with whatever is the right window value for that particular host based on a certain characteristics. The biggest advantage with this solution is actually it's a purely host based solution. You don't need to rely on any shared components, and also it is independent of the ECN signals, which is relied by the congestion control algorithm. To look into the cons, let's look into a little more detail into how that is happening in the next slide. Now comes the biggest question. How do you determine what is the optimum threshold or the optimum window for a specific flow? So this depends on two key parameters. One is the bandwidth delay product. So this brings in what is the capability of the receiver, at what rate can he receive the data. And second is the number of flows that he is supposed to share that bandwidth with. You can see that an optimum threshold would be directly proportional to the BDP, while it will be inversely proportional to the concurrent flows that it's trying to handle. So in order to tackle this and identify this dynamically, we built a tool that basically called as the threshold estimator that helped us to calculate this on every host running as an agent, which we could very easily use for deployment. So the second problem is around enablement or deployment, right? So yes, you could see that unlike congestion control algorithm, which could be rolled out fleet-wide, solutions like this are pretty closely tied to the service because every service has unique traffic characteristics. The number of flows changes. Then the hardware or the NIC they use changes, right? So in order to develop this, we had to build a control plane that could identify what service is running and what would be a great threshold for this specific host in order to avoid network congestion. Let's look at the wins, right? So I'm just taking a specific service here. It's called the feed infra, which is pretty much what, let's say, you open up Facebook, you look at your feed, and this is a service that kind of gets your feed intact, right? So the first chart shows the queue buffer watermark that you use. So I'm looking at two different wins here that's on top of the retransmissions. We saw close to up to 80 to 90% of retransmissions reduced. And on top of that, we also saw 50% of our queues utilizations to go down. So what this translates it to the next chart is basically this gave us a 30% reduction in the SRTT, which eventually translated into latency wins for the services, which we were able to achieve one by reducing retransmissions, also by reducing the queue lengths. Okay, we have seen two interesting problems solved by DC-TCP and receiver window tuning, and let's see what's in the pipeline. The first thing that we saw was based on the supplemental solutions that we built, like receiver window tuning, it's really tough to scale them. So having smart decisions as a part of the congestion control would make us scale much faster, right? So we are trying to customize our congestion control algorithm to handle cases like incast much better, as well as other specific scenarios that we want to handle or customer specific congestion control. The second thing is we have seen that a specific host handling both inter-region and intra-region, depending on two different signals, drops and ECNs, is pretty tough to manage. So we are trying to unify our signal for both the inter-region and intra-region flows, or the short RTTs or the long RTT flows, with just delay-based signal. The third one is we are trying to have a cap or a max cap or a safe threshold rolled out to the entire fleet to max the window that actually each services can flow towards, thereby making sure that the network is safe and we are sharing the network appropriately. So I think with that, thank you very much. I hope the talk was interesting.